A light year is easy to say because both words are familiar. Light year. Together they form a unit of distance so large that the mind tends to turn it back into an abstraction. But there is a simple way to begin. Imagine a pulse of light leaving the neighborhood of Earth and moving outward without interruption. After 1 second, it has crossed nearly 300,000 kilometers. After 8 minutes, it has traveled about as far as the Sun is from Earth. After 1 full year, it has covered about 9.46 trillion kilometers or 5.88 trillion miles. That distance is 1 light year. It is not the distance to another star. Proxima Centauri, the nearest star beyond the Sun, is about 4.25 light years away. 1 light year takes you only part of the way there. If you could stop at that invisible mark and look back, the Sun would no longer be a disk. It would be a star behind you, bright compared with most others, but reduced to a point. The location is also stranger than the phrase interstellar space might suggest. 1 light year is about 63,000 astronomical units. That places the traveler far beyond Neptune, far beyond the Kuiper belt, and within the enormous range often associated with the outer Oort cloud, a distant population of icy bodies whose exact limits remain uncertain. Estimates place that cloud across thousands to perhaps 100,000 astronomical units from the Sun. So even after traveling for an entire year at the speed of light, you could still be moving through the most remote gravitational outskirts of the solar system, rather than arriving at another stellar neighborhood. This is where the scale begins to change the question. If the distance were only a matter of waiting, 1 light year would be simple. Move slowly enough, and eventually the distance disappears behind you. But a human voyage introduces a second clock. A person must remain alive while the ship crosses the gap. The faster the ship moves, the shorter the trip becomes in one sense, yet speed brings new demands. Energy rises sharply. Dust and thin interstellar gas strike with greater force. Radiation becomes harder to manage. The ship must accelerate, coast, navigate, protect its crew, shed waste heat, and, if there is meant to be an arrival rather than a flyby, find some way to slow down again. And beyond a certain speed, time itself no longer agrees between the travelers and the people who remain behind. Relativity does not appear only near black holes or inside equations. Motion changes how much time different observers measure between the same departure and reunion. The effect is tiny at ordinary speeds. Near the speed of light, it becomes part of the architecture of the voyage. So the first light year is not simply a long road drawn through empty space. It is a scale at which distance, velocity, energy, matter, biology, and time begin to press against one another. Every solution changes another part of the problem. More shielding means more mass. More mass means more energy. More speed shortens one clock while changing another. More distance weakens the possibility of immediate help from home. For now, there is no need to choose an engine or imagine a destination. It is enough to hold the measurement itself. 1 year of light, stretched across the space around the Sun, and still not far enough to reach the nearest star. There is no single place where the solar system ends. That may seem surprising. Maps tend to give boundaries clean lines, and the familiar drawings of our planetary system usually stop somewhere beyond Neptune. But the Sun does not surround itself with a wall. Its influence fades through several overlapping regions, each defined by a different piece of physics. A spacecraft traveling outward would therefore leave the solar system more than once, depending on what the word leave is meant to describe. The first great boundary belongs to the solar wind. The Sun continuously releases a thin stream of charged particles into space. Electrons and atomic nuclei flow outward in every direction, carrying part of the Sun's magnetic field with them. Near Earth, this flow passes our planet at hundreds of kilometers per second. Farther away, It continues past Mars, Jupiter, Saturn, Uranus, and Neptune. The particles become thinner as they spread across a larger volume, but they do not immediately disappear. Together, the solar wind and its magnetic field inflate an enormous region around the Sun called the heliosphere. It is less like a rigid shell than a bubble formed by pressure. Inside, conditions are shaped strongly by material coming from our star. Outside, the surrounding interstellar medium becomes dominant. Voyager 1 crossed that boundary in 2012 at a little more than 120 astronomical units from the Sun. It had taken the spacecraft about 35 years to reach it. There was no flash when it crossed. No visible surface passed across the cameras. The transition was recognized through instruments measuring particles and magnetic conditions around the spacecraft. The population of particles associated with the Sun dropped sharply, while energetic particles arriving from the galaxy became more prominent. Humanity had built a talking machine in interstellar space, and yet Voyager had not escaped the Sun. Gravity reaches much farther than the solar wind. Even after the heliosphere has been left behind, the Sun can continue to hold distant objects in orbit. This distinction matters because the outer solar system is not defined by only one influence. A spacecraft can be outside the Sun's particle environment while remaining deep inside the gravitational territory occupied by bodies bound to the Sun. Beyond Neptune, the architecture becomes increasingly sparse. The giant planet orbits roughly 30 astronomical units from the Sun. Beyond it lies the Kuiper Belt, home to Pluto and many other icy worlds. The region contains remnants from the formation of the solar system, preserved at temperatures low enough that volatile materials can remain frozen for immense spans of time. Continue outward, and the recognizable belt thins. Scattered objects follow elongated and tilted paths, some extending hundreds of astronomical units from the Sun. Their orbits preserve evidence of gravitational encounters from the solar system's early history, especially interactions with the giant planets. Then the distances become much harder to visualize. Thousands of astronomical units from the Sun, astronomers expect a different population of icy bodies to begin. This is the Oort cloud. Unlike the Kuiper Belt, which is concentrated roughly around the plane in which the planets orbit, the Oort cloud is thought to surround the inner solar system in a broad, nearly spherical distribution. Its objects are so distant and so faint that the cloud has never been photographed as a structure. Its existence is inferred largely from comets. Some long-period comets enter the planetary region on orbits that carry them from enormous distances. Their paths suggest a reservoir of frozen bodies far beyond the known planets. Over long periods, passing stars, the gravitational field of the Milky Way, and other disturbances can alter the orbits of these remote objects, just enough to send some of them falling inward. A comet may spend most of its existence where the Sun looks like little more than another bright star. Then a small gravitational change begins a fall lasting thousands or even millions of years. Eventually, the comet reaches the warmer planetary system. Frozen material begins turning to gas. Dust is released. A coma grows around the nucleus, and sunlight shapes the familiar tails that can sometimes become visible from Earth. For someone standing beneath that comet in the night sky, it may seem like a visitor arriving from deep space. In a gravitational sense, it may have been a member of the solar system all along. The estimated scale of the Oort cloud is immense and uncertain. Its more distant members may orbit tens of thousands of astronomical units from the Sun, with some estimates extending toward 100,000 astronomical units. That uncertainty is important. There is no surveyed shell of objects marking a measured outer edge. At such distances, the Sun's hold becomes weak enough that the gravity of passing stars and the larger gravitational environment can compete with it. The boundary becomes statistical rather than architectural. Some objects remain attached to the sun, others can be disturbed and lost. Still others may be captured during encounters that unfolded long before humans existed. A light year falls within this enormous scale, so a traveler crossing the first light year from Earth would pass through several different meanings of departure. The planets would be left behind quickly, compared with the full journey. The Kuiper belt would fade into the distance. The heliosphere would be crossed, while almost the entire light year still remained ahead. Then would come a region for which there would be very few obvious landmarks at all. The sun would still exert gravity. Rare icy bodies might remain bound to it. But the density of large objects would be so low that a traveler would not experience the Oort cloud as a field of comets sweeping past the windows. Almost all of the view would be empty space. Even a cloud containing an immense number of objects can be extremely sparse when those objects are distributed through a volume measured in light years. A spacecraft could travel for centuries at ordinary spacecraft speeds without passing close enough to one of these bodies to see it as anything more than a distant point, if it saw one at all. This is one of the recurring difficulties of imagining cosmic distance. Enormous structures do not have to be crowded structures. The solar system can be both immense and mostly vacant. At these distances, the sun's light would also tell the story of separation. Brightness falls with the square of distance. Move 10 times farther from sun, it becomes 100 times weaker. Move 100 times farther and it becomes 10,000 times weaker. By the time a spacecraft is tens of thousands of astronomical units away, sunlight is no longer an abundant source of warmth or practical power. The sun remains visible, but its physical presence has changed. It has become a star. For the first time in the journey, the traveler could look backward and see home reduced to a direction rather than a place. Earth itself would be impossible to distinguish with unaided eyes. The planets would gather into the same tiny region around the distant sun. The entire familiar architecture of days, seasons, moons, and planetary orbits would occupy a patch of space too small to resolve. Nothing dramatic would have happened to it, only distance, and this is the scale hidden inside the first light year. It is long enough for the solar wind to end hundreds of times over, long enough to cross the known planetary system thousands of times, long enough to reach the uncertain country where the sun's most distant companions may circle so slowly that a single orbit can take millions of years. Yet after all of that outward motion, the next star has not arrived. The traveler is still between homes. Distance alone does not tell you how difficult a journey will be. The second number is speed. Once a spacecraft leaves the familiar planetary system behind, the time required to cross 1 light year depends almost entirely on how quickly it can move. And this is where the scale becomes less forgiving, because the fastest machines humans have built are still traveling at only a tiny fraction of the speed needed for a human lifetime to matter. Light crosses 1 light year in 1 year by definition. A spacecraft cannot do that. According to special relativity, any object with mass would require more and more energy as its speed approached the speed of light. Reaching light speed itself would require an unlimited amount of energy. So the practical question is never how to make a spacecraft travel exactly as fast as light. It is how close we might someday be able to get. At 1% of light speed, a spacecraft would need about 100 years to cross 1 light year as measured from Earth. At 10%, about 10 years. At 20%, about 5. At half the speed of light, roughly 2 years. Those numbers sound almost manageable compared with the enormous distances involved. But they hide the most demanding part of the problem. A spacecraft does not simply appear at its cruising speed. It must be accelerated. Imagine a ship leaving Earth and increasing its velocity gradually enough that the people inside remain comfortable. One useful reference is an acceleration similar to the gravity felt at Earth's surface. If a ship could somehow maintain an acceleration of about 1 g, everyone inside would feel something resembling normal weight. The floor would press upward against their feet. Objects would fall toward the rear of the ship. The crew could stand, walk, sleep, and work in an environment that felt much more familiar than microgravity. The sensation would come from acceleration rather than a planet beneath them, but the body would respond to the force. For a while, this sounds almost ideal. The ship accelerates, its speed increases, and day after day, the crew feels something close to Earth gravity. But the energy required to maintain that acceleration rises with the velocity of the ship. The faster the vehicle becomes, the harder it is to add another increment of speed. At ordinary velocities, the familiar equation for kinetic energy works very well. Double the speed, and the energy rises by a factor of 4. At a significant fraction of light speed, special relativity must be included. The ship does not become impossible to accelerate suddenly. Instead, the energy cost grows increasingly steep as the velocity moves closer to light speed. This is one of the places where everyday intuition stops helping. A car can accelerate from 50 to 60 miles per hour without changing the fundamental character of its motion. A spacecraft traveling at 90% of light speed is in a different regime. Adding another 9% does not represent a modest engineering improvement. It represents an enormous increase in energy. There is another reason acceleration matters. Whatever speed the ship reaches on the outbound journey must eventually be removed if the mission is meant to stop. A flyby is easier. The spacecraft can accelerate toward the target, pass through the region at high velocity, gather whatever observations it can, and continue onward. Arrival is different. To arrive means reducing the enormous kinetic energy carried by the ship until its speed becomes compatible with the destination. The energy invested in acceleration does not disappear merely because the journey is nearly complete. The spacecraft has to lose that motion somehow. One possibility is to turn the vehicle around and thrust in the opposite direction. From inside, the crew might feel the same familiar acceleration as before, but now the engine is gradually subtracting velocity rather than adding it. A simple human voyage therefore contains two large energetic events. First, the ship must become fast. Then it must become slow again. And if it carries the fuel for both phases, the problem becomes heavier still, because the fuel needed later must itself be accelerated earlier. That recursive cost has shaped rocket design since the beginning of spaceflight. A rocket carries propellant, but carrying propellant adds mass. More mass requires more propellant, and that additional propellant also has mass. For missions around Earth or through the solar system, engineers already spend enormous effort managing this relationship. At interstellar velocities, it becomes one of the defining constraints. This is why many proposed interstellar concepts try to avoid carrying all of their propulsion energy aboard the spacecraft. One approach is a light sail. Instead of burning fuel, a very thin reflective surface receives momentum from light. Photons have no rest mass, but they do carry momentum. When they strike or reflect from a sail, they can push it. Sunlight can provide that push. A powerful laser can provide much more. If an enormous laser array remained near Earth while a very small spacecraft unfolded a light sail far away, the laser could continue pushing the craft without requiring the vehicle to carry the energy source that accelerates it. The advantage is mass. A tiny probe is easier to accelerate than a crewed ship containing people, water, food, shielding, machinery, spare parts, and life support equipment. The disadvantage is also mass. Human beings cannot be reduced to the size of a microchip. A probe can be designed around grams. A habitat cannot. The difference between those two missions is not simply one of scale. It changes almost every other engineering problem. A small robotic craft might tolerate accelerations that would injure a person. It may not need artificial gravity. It does not need breathable air. It does not need food. It does not need several independent life support systems capable of surviving years without maintenance from Earth. It may even be acceptable for parts of it to fail, as long as enough of the instrument package survives to complete the mission. A crewed spacecraft does not have those freedoms. Its payload is alive, and that fact reaches backward into the propulsion system. More shielding protects the crew but increases the energy required for acceleration. More redundancy improves survival but increases mass. More water supports life and help absorb radiation, but every liter has to be accelerated along with everything else. Even the walls of the living area become part of the propulsion calculation. This is why the first realistic interstellar journeys, if they occur, are likely to look very different from the large inhabited ships imagined in fiction. Physics favors small payloads. Biology favors large protective environments. Interstellar engineering lives between those two preferences, and there is another consequence of speed that begins before the journey is anywhere near complete. Time starts to separate. At ordinary velocities, this separation is far too small for a person to notice. Two clocks can move differently and still remain almost perfectly synchronized for everyday purposes. But special relativity says that observers moving relative to one another do not always measure the same amount of elapsed time. The effect is called time dilation. For someone aboard a fast spacecraft, less time can pass between departure and arrival than passes for someone who remains on Earth. At 10% of light speed, the difference is small. At half the speed of light, it becomes more noticeable. And as the spacecraft approaches light speed, the difference grows rapidly. This does not mean that anyone aboard feels time slowing down. A heartbeat still feels like a heartbeat. A person reads us a minute. A person reads, sleeps, eats, thinks, and ages, normally according to the clock traveling with them. Nothing inside the ship announces that relativity is happening. The difference appears only when clocks following different paths through space-time are compared. A traveler can return from a high-speed journey and discover that more time has passed for the people who stayed behind. The traveler was not frozen. Earth was not accelerated into the future. Both clocks simply measured different amounts of time between the same reunion events. For a voyage of only 1 light year, the difference need not be enormous unless the speed is extremely close to that of light. But the principle changes the meaning of distance. A light year no longer corresponds to one universal travel time. Earth has one clock, the spacecraft has another, and both can be correct. The deeper the journey moves into relativistic speed, the more those clocks separate. That is where 1 light year begins to become something other than a measurement on a map. It becomes a distance that can be crossed through different amounts of lived time, depending on how the traveler moves. And from this point onward, speed will change more than the calendar. It will change the light entering the ship, the energy carried by every particle ahead, and even the appearance of the sky itself. The faster the ship moves, the less familiar the sky becomes. This change would not begin as a sudden distortion. At first, the stars would still seem to occupy the constellations remembered from Earth. But once the spacecraft reached a meaningful fraction of the speed of light, motion itself would begin to reshape the light entering the ship. The first effect is the relativistic Doppler shift. Light has wavelength, and wavelength determines where that light falls across the electromagnetic spectrum. When an observer moves rapidly toward a source, the arriving waves are compressed, their wavelengths become shorter. When the observer moves away, the wavelengths are stretched and become longer. The same basic idea appears with sound. Although sound travels through a medium and light does not require one, a passing siren changes pitch because the spacing of the arriving waves changes. With light, the change is not heard. It appears as a shift in wavelength. At 10% of light speed, the effect is measurable, though the sky would still look broadly recognizable. At higher fractions of light speed, the forward direction becomes increasingly blue shifted, while light arriving from behind is red shifted. A star that normally sends much of its light into visible wavelengths can have part of that light pushed toward ultraviolet from the viewpoint of the spacecraft. At the same time, infrared radiation that human eyes could not normally detect can be shifted upward toward visible wavelengths. The result would not be a simple change from one color to another. Stars emit broad spectra. Detectors aboard the spacecraft would register the redistribution across those spectra far more clearly than human vision alone. There is a second effect happening at the same time. It is called relativistic aberration. Normally, light reaches you from every direction in the sky. But for an observer moving at relativistic speed, the apparent directions from which photons arrive are altered. Light from the sides appears displaced toward the direction of travel. As speed rises, a larger portion of the sky seems to gather forward. The stars themselves have not moved. The change belongs to the geometry of light as measured from the moving spacecraft. Brightness would change as well. Radiation arriving from the forward direction is not only shifted in wavelength, it is concentrated into a smaller apparent region and can appear more intense, while the rearward sky is diminished. The combined result is not a tunnel in the cinematic sense, but a distribution of direction, color, and brightness produced by the spacecraft's motion. If someone had learned the constellations as a child, this might be the first deeply unfamiliar part of the voyage. The stars used for orientation on Earth would no longer draw the same shapes across the windows. A pattern that once stretched widely across the sky could appear squeezed toward the bow. The old map would still contain the right stars, but it would no longer be the right picture. For most of human history, repeated star patterns served as a stable geometry. Sailors crossed oceans by learning where stars rose and set. Travelers recognized direction because the sky returned in familiar forms. A relativistic traveler would carry those memories into a sky transformed by motion. The stars would not have betrayed the map. The traveler would simply be moving in a way no human observer has ever experienced. At 99% of light speed, radiation arriving almost directly ahead is shifted in frequency by a factor a little above 14. Visible light can therefore be pushed well into the ultraviolet, while some infrared radiation can be brought upward toward the visible range. Even at that speed, however, the cosmic microwave background would not suddenly become visible to human eyes. Its radiation begins at wavelengths far too long for a factor of 14 to move it into ordinary vision. It would shift towards shorter wavelengths and become more energetic in the forward direction, but remain primarily in the far infrared. That distinction matters because relativistic travel already gives us enough unfamiliar physics. Without adding effects, the equations do not predict. The real transformation would be striking enough. A spacecraft moving rapidly through interstellar space is not only changing how light arrives, it is also changing how matter arrives. Space between the stars is thin, but it is not empty. The interstellar medium contains hydrogen, helium, electrons, heavier atoms, molecules in some regions, and small grains of solid material. Its density changes greatly from place to place. In the diffuse material around the solar neighborhood, the average number of particles in a cubic centimeter can be only a fraction of one. At ordinary spacecraft velocities, that thinness makes the medium almost irrelevant. At relativistic speed, it does not. The energy of a collision depends on relative velocity. Raise the spacecraft speed high enough, and the same thin gas begins to resemble a weak particle beam aimed continuously at the front of the vehicle. At 10% of light speed, a hydrogen nucleus encountered head-on carries about 5 million electron volts of kinetic energy in the spacecraft frame. At 20% of light speed, the energy is close to 20 million electron volts. At 90%, it rises to roughly 1.2 billion electron volts. The gas has not changed, the spacecraft has. From the crew's frame, atoms that were nearly stationary in the local interstellar medium are now arriving at enormous speed. They strike forward surfaces, ionize material, knock atoms from their places, and create secondary particles. No single hydrogen atom is the central problem. The concern is accumulation. A ship crossing a light year sweeps through an immense column of space. Even a medium containing only a small number of atoms per cubic centimeter can expose the forward surface to a large cumulative fluence over the full journey. The bow therefore becomes a special environment. It cannot be designed like the side wall of a habitat. It is closer to a shield that happens to have a spacecraft behind it. Studies of relativistic probes have modeled erosion, heating, implantation of incoming particles, and damage produced by both gas and dust. For small probes traveling around 20% of light speed, calculations suggest that protective material at the front may need to be sacrificial, accepting gradual erosion so that instruments behind it survive. A crewed vehicle would be harder because its frontal area and required survival margin would. Dust adds another layer. Most interstellar grains are microscopic. Many are far smaller than anything you would notice resting on a table. Their small size helps. But at high relative velocity, even tiny masses carry substantial kinetic energy. Consider a particle with a mass of 1 microgram. At 20% of light speed, its kinetic energy would be on the order of a couple of million joules, comparable to the chemical energy released by a fraction of a kilogram of TNT. A milligram particle, which would be very large compared with common interstellar dust grains, would carry about 1,000 times more energy at the same speed. The point is not that such large grains must be encountered frequently. Larger grains are much rarer. The point is that shielding cannot be designed only for average particles. A long voyage becomes a problem of probabilities. How much material lies along the route? How many grains occupy different size ranges? How much damage can be tolerated? How easily can a shield be replaced or rotated? How much additional mass can be carried before propulsion becomes impractical? The answers are connected. A thicker shield improves protection. A thicker shield also increases mass. More mass demands more energy to accelerate. This is why interstellar vehicle design becomes a network rather than a list of separate problems. Propulsion changes shielding. Shielding changes thermal design. Thermal design changes geometry. Geometry changes the area exposed to incoming material. Even the orientation of the ship matters. During fast cruise, engineers would likely want the smallest practical area facing directly into the direction of travel. Habitat sections could remain behind the forward shield, using the mass already required for protection as a barrier between the crew and incoming particles. Some concepts imagine layered shields. A first layer breaks up or vaporizes an incoming grain. Additional spacing allows the expanding debris to spread before it reaches deeper layers. This general idea is already used against micrometeoroids, although relativistic velocities would require very different materials and dimensions. Charged particles offer another possibility. Magnetic or electric fields can deflect some charged matter, but neutral dust does not respond to a magnetic field simply because the field is present. Physical shielding remains important. And then there is heat. Every impact deposits energy somewhere. Electronics create heat. Power systems create heat. Human bodies create heat. In space, excess heat cannot be carried away by surrounding air. It must eventually leave as thermal radiation. So while the bow may need dense protection, other parts of the ship may need broad radiating surfaces exposed to open space. One part of the vehicle wants to be compact, another wants area. One wants mass in front, another wants as little mass as possible. From inside the habitat, much of this would not be visible. There might be no forward window at all. A window facing the direction of travel would be a weakness in the most heavily protected part of the ship. The changing sky could instead be reconstructed from external cameras and sensors. A display might show the stars crowded forward by aberration. It might translate ultraviolet and infrared back into colors human eyes can interpret. It might mark where the familiar constellations would have been from Earth. And somewhere behind that image, beyond layers of shielding and instrumentation, ordinary hydrogen would continue arriving one particle at a time. The distance would still be 1 light year. But speed would have turned emptiness into weather, and the ship would have to carry its shelter with it. The ship can be protected from dust, and its engines can be designed around the mathematics of relativity. The human body is less easily redesigned. Every person aboard an interstellar spacecraft would carry a biological history shaped by Earth. Bones developed under gravity. Muscles learned to support weight. The cardiovascular system learned to move blood through a body that has a consistent up and down. The inner ear learned to interpret acceleration while standing on the surface of a planet. Remove that environment, and the body begins changing almost immediately. This does not mean the body is failing. In many ways, it is doing what living systems do very well. It is adapting to the conditions that actually exist. The difficulty is that an adaptation useful during the journey may become a liability later. Imagine the ship has finished accelerating and entered a long period of coasting. The engines are no longer producing thrust. Without some other source of artificial gravity, the crew becomes weightless. The first changes are mechanical. On Earth, bones are under load throughout the day. Standing places forces through the hips, legs, and spine. Walking produces repeated stress. Even remaining upright requires the skeleton to carry the body continuously. Bone responds to that loading. It is living tissue, constantly being broken down and rebuilt. Cells called osteoclasts remove old bone. Osteoblasts create new material. Under normal conditions, the two processes remain in a shifting balance. In microgravity, that balance changes. The skeleton no longer needs to support body weight. Mechanical signals that help maintain dense weight-bearing bone are reduced. Over time, bone mineral can be lost, particularly from regions such as the hips, legs, and lower spine. Exercise can slow the process. It does not recreate Earth perfectly. Astronauts living aboard orbital stations spend considerable time using resistance machines, treadmills, and stationary bicycles. Because remaining physically active is part of maintaining the body itself. On an interstellar ship, exercise would not be recreation. It would be maintenance. The crew would be maintaining the vehicle, and at the same time, maintaining themselves. Muscle responds in a similar way. On Earth, large groups of muscles perform work that is so ordinary it rarely enters awareness. The muscles of the legs keep the body standing. The back stabilizes the spine. The abdomen contributes to posture. Small adjustments happen continuously while walking, turning, sitting, and reaching. In weightlessness, much of that demand disappears. A person can move across a cabin with a small push from a fingertip. An object with the mass of a heavy suitcase no longer needs to be lifted from the floor. Its mass remains, but its weight has vanished. The body notices that difference. Muscles that are no longer asked to produce their usual force begin to reduce in size and strength. Exercise can provide replacement loading, but the entire daily environment is still different from life on Earth. Then the fluids begin to move. Gravity normally pulls blood and other fluids toward the lower body. The cardiovascular system has spent a lifetime compensating for that pull. Remove gravity, and fluid shifts upward. The face can become slightly fuller. Pressure patterns change around the head and chest. The body interprets some of this redistribution as excess fluid and adjusts the total volume it maintains. The heart also finds itself working in a different environment. It no longer has to push blood upward toward the brain in the same way it does when a person is standing on Earth. Again, the body adapts. And again, the adaptation can create trouble when gravity returns. After months in orbit, astronauts may experience difficulty standing immediately after landing. Blood can move toward the legs faster, and the cardiovascular system can compensate. Blood pressure falls. Dizziness can follow. A person returning from a much longer period without gravity might face a more difficult transition. For a journey lasting years, no direct human experience exists. No one has spent 10 years continuously in microgravity. At that point, medicine would be moving beyond observation and into extrapolation. The uncertainty itself becomes part of the mission design. There are changes in the eyes as well. Has revealed that microgravity can affect the shape of the eye and the tissues around the optic nerve in some astronauts. The condition is associated with fluid shifts toward the head and is often discussed under the broader term spaceflight associated neuroocular syndrome. Not every astronaut experiences the same changes. Not every change persists after returning to gravity. But for an interstellar crew, vision would be too important to treat as a secondary concern. A person might need to inspect a hairline fracture in a pipe, read a diagnostic display, guide a repair tool into a narrow opening, perform a medical procedure on another crew member. A small decline in vision on Earth can be inconvenient. On a spacecraft with no repair team coming from outside, small losses can become operational problems. The body also carries another vulnerability that is harder to see: radiation. Earth protects life in two important ways. The atmosphere absorbs and scatters much of the energetic radiation arriving from space. Earth's magnetic environment also influences the paths of many charged particles. Beyond the protective influence of our planet, astronauts receive greater exposure. Far into interstellar space, a crew would be surrounded by a continuing background of galactic cosmic rays. These particles are mostly atomic nuclei moving at very high energies. Many are protons. Some are nuclei of heavier elements. They travel through the galaxy after being accelerated by energetic astrophysical processes. And because they arrive from many directions, there is no simple way to point the ship away from them. The forward shield, designed for dust, cannot solve the entire problem. Radiation shielding has to surround the inhabited parts of the vehicle. Material matters. Hydrogen-rich substances can be useful because they tend to produce fewer damaging secondary fragments than some heavier structural materials when struck by high-energy particles. This gives water an interesting second role. The crew already needs it. Stored in carefully arranged tanks, some of that water can also contribute to radiation protection. Food supplies and other hydrogen-rich materials can be positioned around living areas for the same reason. The ship begins to acquire a layered design. Outside is structure. Inside that may be machinery and storage. Deeper still, protected by useful mass wherever possible, are the spaces where people spend most of their time. A sleeping cabin might be placed where the geometry provides more shielding. A central refuge could contain additional water and supplies, giving the crew a more protected location during periods of increased radiation exposure. Every kilogram, once again, has more than one job. Water is something to drink. It can be part of the thermal system. It can be radiation shielding. It may help stabilize the mass distribution of the vehicle. The farther the ship travels, the less attractive single-purpose mass becomes. There is a quieter problem underneath all of these biological changes. The body does not experience the spacecraft as a temporary environment. Biology has no concept of the mission plan. It does not know that the crew intends to arrive somewhere later. It responds only to conditions now. If gravity is absent, bones adapt to the absence of gravity. If the muscles are lightly loaded, they adapt to lighter work. If day and night are artificial, the circadian system must build its rhythm from the signals provided aboard. This means the habitat cannot be treated as a container. It becomes part of human physiology. Lighting has to support a stable daily rhythm. Exercise equipment has to reproduce enough mechanical load to preserve strength. Air must be circulated so that exhaled carbon dioxide does not linger around a sleeping person's face. Humidity must be controlled, water must be recovered, waste must be processed, microbes must be monitored. A terrestrial building can tolerate a surprising amount of inefficiency because the surrounding environment supplies fresh air, water, food, and a place for waste to go. An interstellar spacecraft has no surrounding ecosystem to borrow from. It must carry an artificial one. The closer that system comes to recycling its own resources, the less material must be launched at departure. But perfect recycling does not exist. Filters degrade, pumps wear, seals leak, chemical compounds accumulate in unexpected places. Microorganisms adapt to surfaces, sensors drift out of calibration. A system designed for decades cannot simply be efficient. It must remain repairable. That creates a different philosophy of technology from the one used for many objects on Earth. A household appliance can fail and be replaced. A spacecraft 1 light year from home cannot order another machine. The crew must understand enough of the habitat to keep it alive. Components may need to be standardized so that one part can substitute for another. Manufacturing capability aboard the ship could allow simple replacement pieces to be created from stored material. Software would need redundant systems and methods for recovery that do not depend on a live connection with engineers on Earth. Knowledge itself becomes cargo. Engineering manuals, medical references, agricultural information if food is being grown, diagnostic procedures, scientific models, instructions for systems that may not fail until years after launch, when the people who designed them are no longer available in any useful real-time sense. And somewhere within that machinery, there must still be room for an ordinary human day. Someone wakes, someone eats, someone exercises, someone repairs a valve, someone watches a film made on Earth, someone notices that the same wall has been beside the same table for hundreds of days. The scale of 1 light year is usually introduced through distance, but inside the ship it would also be experienced through repetition. The same corridors, the same voices, the same mechanical sounds, the same small community continuing while an almost empty landscape passes outside. For much of human history, long journeys also depended on small communities living inside limited worlds. Ocean voyages once carried crews beyond immediate help for months. Remote observatories and polar stations still create periods when weather and distance narrow the number of people available. The comparison only goes so far. A ship between stars would have no nearby shore. But the older lesson remains useful. Survival in an isolated environment is not only a matter of keeping individual people healthy, it depends on maintaining the small society formed between them. Privacy matters, routine matters, conflict has to be managed, sleep matters, crew members need enough common purpose to cooperate and enough personal space to remain themselves. Communication with Earth can continue, but distance gradually changes what communication means. When the ship is 1 light hour away, a message needs 1 hour to return home. At 1 light day, it needs a day. At 1 light month, a month. There is nothing a better antenna can do to remove that delay. The limitation is not signal strength, it is the speed of light. A message sent from 1 light year away needs 1 year to reach Earth. If someone on Earth replies immediately, the answer requires another year to return. A simple exchange takes 2 years. No conversation can remain a conversation in the ordinary sense across that distance. The crew can still send recordings, families can still answer, scientific data can still travel home. But everyone is communicating with earlier versions of one another. A message arriving aboard the ship describes Earth as it was a year before. The response sent back will be read a year later still. The connection survives, but the present moment is no longer shared. There may be a strange calm in its celebration as well. At night aboard the ship, if the crew still uses the word night, someone could lie inside a protected cabin while pumps move water through the walls and air circulates through filters overhead. The machinery would be close. Beyond it would be shielding. Beyond the shielding, interstellar space. And somewhere behind the ship, too far away to appear as anything more than a star, would be the place where the human body first learned what gravity felt like. Crossing 1 light year would not require leaving that history behind. It would require carrying as much of Earth as the body still needs. If a human body needs something like Earth to remain healthy, one possible answer is not to carry gravity across interstellar space. It is to manufacture the sensation of gravity from motion. A spacecraft can rotate. Inside a rotating habitat, the floor curves around a central axis. A person standing against that floor is continually being redirected toward the center of rotation. The floor presses against the body, and from inside the habitat, that pressure can feel like weight. Nothing is pulling the crew downward in the way Earth does. The effect comes from acceleration, but bones and muscles respond to forces rather than to the philosophical reason those forces exist. If the rotation is designed well, standing on the inner surface of a large ring could provide continuous mechanical loading while the ship itself moves through space. This idea is older than human spaceflight. Long before anyone spent months in orbit, engineers and physicists understood that rotation offered a way to create artificial gravity without inventing new physics. The difficulty was never whether the principle worked. The difficulty was deciding how large the structure should be. A small habitat has to rotate quickly to produce a strong acceleration at its floor. A larger habitat can rotate more slowly. That matters because the human balance system notices rotation. The inner ear contains fluid-filled structures that help the brain interpret motion and orientation. In an ordinary room on Earth, turning the head while standing does not significantly change the direction of gravity. Inside a rapidly rotating habitat, moving the head or walking toward the axis changes the motion of the body relative to the rotation. Those changes can produce Coriolis effects. A person might turn their head and briefly feel that the room is moving in an unexpected direction. A thrown object can follow a curved path relative to the rotating floor. Walking with the direction of rotation can feel slightly different from walking against it. The larger and more slowly rotating the habitat becomes, the less intrusive many of these effects can be. So comfort favors size, propulsion favors the opposite. A ring wide enough to provide a familiar gravitational environment needs structural material. It needs floors, supports, pressure walls, air circulation, plumbing, power cables, emergency systems, and bearings or other mechanisms if part of the spacecraft rotates while another part remains fixed. Every piece adds mass, and every piece of mass must share the journey. The propulsion system does not care whether a kilogram belongs to a fuel tank, a medical cabinet, a radiation shield, or the wall of a bedroom. To the engine, it is a kilogram. It must be accelerated. If the ship intends to stop, it must later be decelerated. This is where interstellar design begins to behave less like a collection of inventions and more like an ecosystem of compromises. Artificial gravity helps the body. It makes the ship heavier. Radiation shielding helps the body. It makes the ship heavier. Redundant machinery helps the crew survive failures. It makes the ship heavier. Larger living spaces may help psychological health. They make the ship heavier. There is no single engineering department that can solve its own problem without changing everyone else's. The habitat designer changes the propulsion problem. The propulsion designer changes the thermal problem. The thermal engineer changes the shape of the vehicle. The shape changes how much frontal shielding is needed. The shield changes the mass, and the mass returns to the engine. A successful interstellar spacecraft would therefore be less like a machine assembled from independent systems and more like a tightly balanced physical argument. Every part would have to justify its presence. This does not necessarily mean making everything fragile or minimal. Quite the opposite. A machine traveling far enough that replacement parts cannot arrive must be unusually tolerant of failure. On Earth, redundancy often looks inefficient. Two pumps where one normally works, several computers doing the work of one, duplicate communication paths, backup valves that may never open. On a distant spacecraft, inefficiency can be survival. But true redundancy means more than carrying identical copies. If three identical pumps share the same hidden design flaw, all three can fail in the same way. A long-duration vessel would benefit from systems that can fail differently. Different sensing methods, different control paths, manual overrides, components that can be repaired rather than sealed permanently. The ability to isolate one section of plumbing while another remains active, electrical networks that can be divided when a fault appears. A habitat that can lose one compartment without losing the atmosphere of the entire ship. Redundancy becomes architecture, and architecture becomes mass. There is no escaping the exchange. Some of that mass can serve several purposes at once. Water can surround occupied spaces and contribute to radiation shielding. Food stores can be placed where their material adds protection. Structural walls can contain equipment, rather than separating storage from shielding. Waste products may remain useful as radiation mass until they are processed. The shape of the spacecraft can place machinery between the crew and directions of greater expected particle exposure. The idea is not to make the ship lighter by removing everything. It is to make each kilogram work harder. Power requires the same kind of thinking. Close to the sun, solar energy is abundant enough that many spacecraft can live from panels spread into sunlight. Far from the sun, that arrangement loses its usefulness. Sunlight follows the inverse square law. Double the distance, and a surface receives 1/4 of the solar intensity. Move 10 times farther away, and the intensity falls to 1/100th. At 1 light year, the sun is tens of thousands of times farther away than it is from Earth. Its light remains visible. Its energy is spread across billions of times larger. A human interstellar ship could not expect ordinary solar panels to support its life systems there. It would need an internal power source. Whatever that source might be, it would have to operate for the duration of the voyage with a level of reliability rarely demanded from machines on Earth. Power would circulate air, run pumps, control temperature, recycle water, operate navigation instruments, maintain computing systems, support food production, if part of the diet were grown aboard, power medical equipment, and keep the environment within the narrow range in which human biology functions well. But generating power creates another substance that cannot simply be discarded. Heat. A spacecraft is surrounded by vacuum. and vacuum is a poor place to lose heat quickly. There is no surrounding air to carry warmth away through convection. There is no ocean flowing past the hull. Ultimately, unwanted thermal energy must leave as electromagnetic radiation. That makes radiators part of the life support system. They may look simple compared with an engine, but they carry an important responsibility. Heat from electronics, people, lights, pumps, and the power plant has to travel into those surfaces and then radiate into space. If heat production exceeds the ability to reject it, internal temperatures rise. A spacecraft can freeze if it lacks power. It can also overheat while surrounded by space that is only a few degrees above absolute zero. The cold outside does not automatically cool the inside. There has to be a path for energy to leave. Larger radiators can shed more heat. Higher radiator temperatures can also increase the rate at which energy is emitted. But radiators must be built from something. They need plumbing or conductive structures. They need protection from damage. And they must be positioned where they can radiate effectively without being hidden behind other warm parts of the spacecraft. Once again, geometry becomes connected to mass. A rotating habitat may prefer one shape. A forward dust shield prefers another. Radiators want clear views of space. Engines need their exhaust directed away from structures. Antennas need useful lines of sight. Sensors need fields of view. The final vehicle, if one is ever built, may look unfamiliar, not because designers wanted a futuristic appearance, but because the physics selected the shape one compromise at a time. There is also the question of motion itself. During periods of powered acceleration, the crew may already feel an effective downward direction. If the acceleration is strong enough and sustained long enough, rotation may not be needed during that phase. But most plausible propulsion concepts do not provide Earth-like acceleration continuously for years. A ship may spend long periods coasting. The rotating habitat becomes most valuable there. This raises another design question. Does the entire spacecraft rotate, or only the inhabited section? Rotating the whole vehicle may simplify the interior experience, but large engines, radiators, antennas, and forward shields may not benefit from rotation. Keeping those sections stationary, while the habitat spins, introduces moving interfaces. Power has to cross between rotating and non-rotating structures. Fluids may have to cross. Data has to cross. Mechanical bearings or magnetic couplings must operate for years. A system created to solve one biological problem has now created several engineering ones. There are more imaginative layouts. 2 habitat modules might be connected by long cables or booms and rotate around a common center, reducing the amount of rigid structure needed. A spacecraft could extend the living sections outward after acceleration and retract them before major maneuvers. The required radius could be changed during the journey. Each approach trades structural complexity against mass, control, reliability, and human comfort. None removes the underlying relationship. Interstellar travel is difficult, partly because the obvious solutions are rarely free. A shield protects you by becoming something the engine must move. A spacious habitat protects you by becoming something the structure must support. A backup system protects you by consuming resources even when it is never used. A radiator keeps the ship cool by becoming another surface exposed to damage. The design does not approach perfection by eliminating these costs. It approaches viability by balancing them. And there is something familiar in that kind of engineering. The first ocean-going vessels that crossed beyond sight of land also carried small enclosed worlds. Water, food, repair materials, navigation knowledge, medical knowledge, and the tools needed to keep the vessel functioning had to travel with the crew. Those ships depended on wind and wood rather than relativistic propulsion and radiation shielding. The physical scale was entirely different, but the underlying idea was recognizable. When the shore can no longer help you, the vessel becomes more than transportation. It becomes the environment in which the journey is possible. A spacecraft crossing 1 light year would take that principle farther than any vessel before it. The air would belong to the ship. The gravity might belong to the ship. The water cycle would belong to the ship. The comfortable temperature of a sleeping cabin would exist because machines were continuously moving energy through pipes, walls, radiators, and power systems. Even the direction called down might be an engineered property of the room. Outside, there would be no floor and no ceiling. Inside, a cup could rest on a table. A person could walk along a curved corridor and feel their own weight. And for a little while, within a structure moving between stars, physics could be arranged into something that felt almost like home. Far from Earth, another familiar idea begins to change. Navigation. On a road, position is defined by landmarks that stay where they are. At sea, coastlines, stars, and instruments can tell a navigator where the vessel has moved. Even a spacecraft traveling among the planets can compare its trajectory with objects whose positions are known with remarkable precision. Between stars, the same principle still works, but the reference frame becomes larger. The destination is moving. The sun is moving. The stars used for orientation are moving, and the spacecraft itself is crossing the galaxy along a path that has to be predicted years in advance. Suppose a mission is aimed toward a nearby star. The spacecraft cannot simply point toward where that star appears in the sky. At departure, the light reaching Earth from the star is already old. If the star is several light years away, the image being observed shows where it was several years earlier. Meanwhile, the star has continued, moving through the galaxy. Its motion across the sky can be measured as proper motion. Its movement toward or away from the sun can be measured as radial velocity. Combine those measurements with distance, and astronomers can estimate how the star is moving through three-dimensional space. That motion may appear tiny from Earth. Over the duration of an interstellar voyage, tiny changes accumulate. A spacecraft must therefore aim not for the star that appears in the telescope now, but for the region of space where the star is expected to be when the spacecraft arrives. In that sense, an interstellar trajectory is partly a meeting appointment. Two moving objects begin separated by light years. The navigation system predicts where their paths can intersect. This is not unfamiliar mathematics. Space agencies already navigate probes toward planets that are moving around the sun. A mission to Mars does not aim at the point where Mars is seen when the rocket launches, follows a trajectory calculated to arrive where Mars will be later. Interstellar navigation extends the same logic across a much longer baseline. The distances are greater, the travel times are longer, and small errors have more room to grow. A spacecraft that departs with a tiny angular error can end up extremely far from its intended line after traveling a light year. So the vehicle must keep measuring. It needs to know not only where the destination is, but where it is. That second question becomes interesting once Earth is too distant to function as a real-time guide. Radio tracking from the home system could continue for a long time. Large antennas could measure the direction and timing of signals from the spacecraft. The spacecraft could also receive navigation updates, but every update would describe an earlier state. The farther the ship travels, the older every observation becomes by the time it reaches the other side. At 1/10 of a light year from Earth, a signal needs more than a month to cross the distance. At half a light year, about 6 months. At 1 light year, 1 full year. Navigation cannot depend on asking Earth what to do next whenever a correction is needed. The ship must become increasingly autonomous. Fortunately, the galaxy contains its own reference points. Stars provide one set. A navigation system can compare observed positions with a stored map, account for the spacecraft's velocity, and estimate orientation. But stars are not perfectly fixed pins on a celestial sphere. Their apparent direction depend on the motion of the observer. And at relativistic velocity, the aberration of light must be included. The sky seen from the ship is altered by speed, so the computer has to transform the observed sky back into a useful navigational frame. It must know how fast the ship is moving. It must understand how that motion shifts apparent star positions. Then it can recover the underlying geometry. Another class of objects offers a different kind of reference. Pulsars. A pulsar is a rotating neutron star whose beams of radiation can sweep past Earth or past a spacecraft in repeated pulses. Some rotate with remarkable stability. That regularity allows certain pulsars to function as natural clocks distributed across the galaxy. If a spacecraft observes several of them and compares the arrival times of their pulses with predictions stored aboard, differences in timing can help constrain the spacecraft's position. The idea resembles navigation systems used on Earth. A terrestrial receiver determines position by comparing precisely timed signals. A future interstellar craft could use distant astrophysical sources instead. No satellite constellation has to be carried ahead. The clocks are already in the sky. The ship only needs to read them accurately. This does not make the problem trivial. Pulsar signals can be faint. Detectors require mass and power. The timing models must remain accurate. Relativistic corrections must be included. But among the obstacles of interstellar travel, navigation is unusual because the laws of physics provide useful reference signals rather than placing a fundamental barrier in the way. The challenge is measurement. That distinction matters. Propulsion asks for enormous energy. Radiation protection asks for mass. Long-duration biology asks questions for which human data remain incomplete. Navigation asks whether the spacecraft can observe carefully enough and calculate accurately enough. Human beings have been solving versions of that problem for a very long time. Long before radio navigation, atomic clocks or spacecraft, people learned to cross open water by treating the sky as a working instrument. A star rising at a known point on the horizon could indicate direction. Repeated patterns could mark seasons. The height of familiar stars above the horizon could help a navigator understand latitude. Knowledge of currents, winds, clouds, birds, and ocean swells completed the picture. The navigator did not need the sky to be close, only dependable. A future ship between stars would operate on a different physical scale, using sensors and relativistic mathematics rather than an unaided eye. But the relationship would still be recognizable. Position would be found by comparing the vessel with the larger world around it. For the interstellar crew, that larger world would be the galaxy. And once navigation becomes independent, another transition occurs. The crew is no longer simply traveling away from Earth. They are operating a vehicle that Earth cannot directly control. Consider a minor failure in a guidance system when the ship is several light months away. A diagnostic report can be transmitted home. Engineers on Earth can study it. They can propose a solution. But the crew may have repaired the problem long before the first answer arrives. If the failure threatens the trajectory immediately, waiting is not an option. The people aboard must understand the systems well enough to make their own decision. That changes the purpose of communication. Near Earth, communication can support operations in real time. Farther away, communication becomes consultation with delay. Farther still, it becomes an exchange of records. Mission control no longer controls the mission. It advises a past version of it. This shift would happen gradually. There would be no exact morning when the crew announced that Earth was no longer useful. Instead, the delay would lengthen a little more each day. At first, A technical question might receive an answer within hours, later, days, then weeks. Eventually, a crew member could send a detailed description of a system failure, repair the system, monitor the repair, discover a second problem, solve that problem too, and move on with the mission before Earth had even received the first message. By the time a reply arrived, it would belong to history. The same would be true of ordinary human messages. A recording from a friend on Earth would still carry a voice, a face, a room, perhaps the sound of rain against a window or traffic beyond a wall. But the moment preserved in that recording would be gone. Months might have passed since it happened. Later, in the voyage, a year, the crew could answer, knowing that their response would make the same journey in reverse. The connection would remain real. It would simply no longer occupy the same present. There is a subtle difference between being far away and being unable to share the same now. Interstellar distance creates both. For the people aboard, this places more weight on the small community inside the ship. Medical decisions cannot wait. Engineering decisions cannot wait. Course corrections cannot wait. Disagreements cannot always be handed to someone outside the crew for immediate resolution. The ship becomes its own operational world. That may be one of the least visible demands hidden inside 1 light year. Not speed, not radiation, not fuel, competence. The people traveling that distance would have to carry enough knowledge, training, and trust to act without supervision across situations that no mission planner could predict completely. The computers could help. Automation could monitor thousands of variables at once. Artificial intelligence could assist with diagnosis and planning. But hardware can fail. Software can encounter conditions its designers did not anticipate, and decisions involving human health or competing risks may still require judgment. A crew crossing interstellar space would therefore need something rare in modern technological life: the ability to remain technologically advanced while becoming operationally self-contained. They would carry centuries of accumulated knowledge in machines and databases, and they would use it without expecting anyone nearby to answer the phone. Outside, the stars would continue moving in their own directions around the Milky Way. The spacecraft would measure them. Pulses from distant neutron stars would arrive on schedule. The navigation computer would compare one signal with another and revise its estimate of position. A small engine firing might adjust the trajectory by a fraction of a degree. Nothing about the correction would feel dramatic, but over a light year, a small correction made early could determine where the ship eventually goes. The first navigators crossed seas by learning to trust patterns spread across the sky. An interstellar crew might cross the first light year by doing something surprisingly similar. They would keep looking outward to understand where they were. Knowing what 1 light year demands is not the same as knowing how to cross it. But the difference between those two ideas is smaller than it once was. There are parts of the problem we understand very well. Relativity tells us how clocks behave at high velocity. Classical and relativistic mechanics tell us how much kinetic energy a spacecraft carries. Radiation physics tells us how energetic particles interact with shielding. Astronomy tells us what kind of material occupies the space between stars. What remains uncertain is whether all of those requirements can ever be assembled into one working vehicle. For more than half a century, engineers have explored pieces of that question. Some of the earliest serious studies began with nuclear energy. In the late 1950s, Project Orion examined a propulsion system that would have accelerated a spacecraft using a sequence of nuclear explosions behind a large pusher plate. The concept sounds severe because the individual energy releases were severe. But the study itself was an engineering effort based on known physics. Each explosion would push against the plate. Shock absorbers would reduce the sudden impulse transmitted to the vehicle. Then another device would detonate, and another, repeated thousands of times. Those impulses could gradually accelerate a very massive spacecraft to velocities far beyond those achievable with chemical rockets. Orion never became an interstellar vehicle. Political, environmental, and practical limitations ended the program before anything close to the proposed large spacecraft was built. But it demonstrated an important idea. When chemical propulsion becomes too limited, interstellar thinking does not require abandoning physics. It requires finding a more concentrated source of energy. Fusion became one of the next possibilities. During the 1970s, the British Interplanetary Society studied a concept called Project Daedalus. Daedalus was not designed for human passengers. It was an unmanned probe. That distinction allowed the designers to avoid habitats, artificial gravity, large crew shielding systems, food, medical supplies, and most of the machinery needed to keep human beings alive. Even after removing those requirements, the proposed spacecraft was enormous. Its propulsion system would use repeated fusion reactions involving small fuel pellets. The goal was to reach a significant fraction of the speed of light and cross several light years within a human lifetime. The study did not claim that such a spacecraft could be built immediately. Its purpose was narrower and perhaps more valuable. It asked what a physically consistent interstellar probe would require if designers were limited to technologies that did not violate known laws of nature. The answer was demanding. Large amounts of fuel, high-performance materials, reliable fusion ignition, precision navigation. A vehicle capable of operating for decades without repair from Earth. But there was no single place in the design where the equations said the journey was forbidden. That distinction continues to shape interstellar research. Impossible and extremely difficult are not the same category. One is a statement about physical law. The other is a statement about capability. Light speed travel for a massive spacecraft belongs to the first category under our present understanding of relativity. A probe moving at a fraction of light speed belongs to the second. More recent concepts have responded to the mass problem by shrinking the spacecraft. Instead of accelerating thousands of tons, accelerate grams. A small probe attached to a thin reflective sail could, in principle, be pushed by a powerful laser array located near its home system. The spacecraft does not need to carry most of the energy source. The laser remains. Behind, photons cross the distance between the array and the sail and transfer momentum when they arrive. The acceleration phase can therefore happen without loading the probe with enormous propellant tanks. This is the basic idea behind concepts such as breakthrough starshot. The proposed probes are not inhabited spacecraft. They are closer to flying instrument packages. That is the point. Mass is so costly at interstellar velocity that removing kilograms can transform the scale of the problem. A probe weighing only a few grams can tolerate conditions that would be unacceptable for a crew. It can accelerate rapidly. It does not require life support. It does not need years of food. And if the mission is a flyby, it does not necessarily need to stop. But shrinking the vehicle creates new difficulties. A tiny spacecraft has limited power. Its communication system must send information across light years using very little energy. Its instruments must survive acceleration and years of exposure to space. The sail has to remain stable while an intense beam pushes it. The laser system would have to hold its aim across great distance with remarkable precision. And after acceleration ends, the probe still has to navigate toward a target, moving through space years into the future. The problems change. They do not disappear. Still, this shift towards small interstellar probes suggests something about how the first true crossing may happen. Humanity may not begin by sending people. It may begin by sending instruments that would follow a pattern already familiar from exploration. Robotic spacecraft reached the moon before astronauts did. Machines visited Venus and Mars before any human could. Probes crossed the asteroid belt, flew past the giant planets, entered orbit around Saturn, landed on a comet, touched asteroids, and traveled beyond the heliosphere. Again and again, instruments go first, because they can survive journeys that people cannot yet make. The first spacecraft, built specifically to cross a light year, may belong to the same tradition. It might carry no cabin, no beds, no windows, no artificial gravity. Only a sail, sensors, navigation hardware, communication equipment, and enough intelligence to continue functioning when Earth has become too distant to supervise it directly for the engineers who designed such a machine. The journey might outlast part of their own lives. That is another feature of interstellar work that rarely appears in the equations. The timescales begin to exceed individual careers. A propulsion researcher may contribute to a system whose final version is built decades later. A materials scientist may solve a shielding problem for a spacecraft they never see launched. An astronomer may refine the position of a target whose eventual visitor is designed by people not yet born. The knowledge moves forward even when the people do not. Astronomy has always contained some of this generational structure. One observer measures a star, another improves the measurement. A later generation discovers that the star has a planet. Still another builds an instrument capable of studying the planet's atmosphere. No single person completes the chain. The work passes quietly from one set of hands to another. Interstellar travel may demand the same patience on a larger scale. For now, humanity lives in a period when the map is ahead of the vehicle. We can calculate the path. We can describe the relativistic effects. We can estimate the shielding problem. We can model the communication delay. We can predict where nearby stars will be. And yet the machine capable of carrying a person across 1 light year does not exist. There is something useful in that gap. It reveals how science often moves. Understanding does not always arrive after experience. Sometimes the equations reach a place before we do. Relativity described time dilation before astronauts carried precision clocks into space. Orbital mechanics described paths between worlds centuries before spacecraft traveled them. Nuclear physics existed before engineers learned to build controlled reactors. The mathematics of 1 light year is already here. The engineering is still catching up, and perhaps that is the most realistic way to imagine the first interstellar crossing. Not as a sudden leap, not as one invention appearing fully formed, but as thousands of smaller improvements accumulating across propulsion, materials, computing, astronomy, medicine, and power generation. A lighter structure, a better radiation shield, a more stable fusion reaction, a more efficient laser, a stronger sail, a navigation system that can work without Earth, a life support component that lasts longer than the one before it. Each improvement may seem modest by itself. Together, over generations, they could change what distances are practical. 1 light year will not become shorter. The speed of light will not change. The energy equations will not become more forgiving. The interstellar medium will still occupy the path. What can change is the kind of machine that enters it. And somewhere in the future, a small object made on Earth may pass the invisible distance that light covers in 1 year. There may be no marker when it happens, no boundary glowing in space, only a number inside a navigation system quietly changing from slightly less than 1 light year to slightly more. Behind it, the sun will still be visible. Ahead, the stars will still be far away. But for the first time, something built by human hands will have carried the full measure of that distance with it. 1 light year never changes. It remains the same distance whether a person crosses it, a probe crosses it, or nothing crosses it at all. The measure belongs to light itself, how far it travels through vacuum during 1 year. What changes is everything required to follow. From Earth, a light year can look like a single number written beside a star. From inside a spacecraft, that number would unfold into thousands of decisions. How quickly to accelerate, how much energy to carry or receive from elsewhere, how much shielding is enough, how much mass can be afforded, how to remove heat, how to preserve a human body through years of confinement, how to navigate when every useful landmark is moving, how to make decisions when an answer from home arrives long after the question has changed. None of these problems exists because space is resisting the traveler. Space is doing almost nothing. That may be the strangest part. There is no ocean pushing against the hull, no atmosphere producing drag, no mountain range blocking the route. For almost the entire crossing, the spacecraft moves through a medium so thin that a human being would call it empty, and still the journey is difficult. The difficulty comes from carrying matter across such a large distance quickly enough for human time to remain relevant. Speed turns thin gas into energetic impacts. Speed turns microscopic dust into a shielding problem. Speed raises the energy stored in the moving spacecraft. Speed changes the relationship between clocks. The distance itself is passive. Velocity makes it demanding. That is why 1 light year can belong to 2 very different kinds of future. One future moves slowly. A durable robotic craft could leave the solar system and continue for thousands of years. It would not need to protect a human lifetime. It would only need to remain functional long enough for machinery, navigation, and communication to endure. The other future moves quickly. That's the future in which a person could depart and still expect the journey to fit somewhere within a human life. It is also the future that asks the most from physics and engineering. Between those possibilities lies a wide range of missions. Tiny laser-driven probes, fusion spacecraft, vehicles that never slow down, machines designed to carry scientific instruments rather than people. Perhaps, much later, inhabited craft whose shape would be determined less by imagination than by shielding, heat rejection, artificial gravity, propulsion, and the need to repair almost everything aboard. There is no reason to expect the first successful design to resemble the spacecraft we know today. Aircraft did not resemble ocean ships. Ocean ships did not resemble carts. A machine built specifically for interstellar space may eventually develop its own logic. Its forward face may be dominated by protective material. Its habitat may rotate. Its radiators may stretch outward into regions protected from the main direction of travel. Its propulsion system may remain far behind the inhabited section. The crew may never see directly through the bow at all. What they call a window could be built from sensors mounted beyond the shielding. The world outside would then arrive as data before it became an image. That would not make the journey less real. Human beings already experience much of the universe this way. Radio telescopes translate wavelengths our eyes cannot see. X-ray observatories turn high-energy photons into maps. Infrared detectors reveal cool objects hidden from ordinary vision. Spacecraft transmit numbers across billions of kilometers, and computers reconstruct landscapes no human observer has stood upon. Interstellar travel would extend a habit we already have. First, we learn how to measure a place. Then, we learn how to send something there. Only much later do we ask whether a person can follow. For 1 light year, we are still mostly in the first stage. We can describe the distance precisely. We can measure nearby interstellar material. We can test relativity. We can observe how bodies change during months in microgravity. We can operate machines beyond the heliosphere. We can calculate the trajectories of nearby stars and imagine navigation systems that use the galaxy itself as a reference. These pieces do not yet form a human interstellar vehicle. But they are not disconnected pieces. They belong to the same problem. That may be why 1 light year is such a useful distance to consider. It is far enough to expose nearly every major difficulty of interstellar travel without requiring us to imagine reaching another star. You do not need to travel 4 light years to discover the propulsion problem. You do not need to arrive at Proxima Centauri to encounter communication delay. You do not need another planetary system to make radiation, mass, heat, isolation, and relativity matter. The first light year already contains all of them, and after crossing it, the traveler would still have an unusual view ahead. No nearby sun filling the sky, no destination world becoming larger through the window. Proxima Centauri would remain more than 3 light years away. The traveler would be farther from Earth than any human-built object has ever been by an almost unimaginable margin, and yet still much closer to home, the star, than to another. Behind the ship, the sun would appear as a bright point. Around that point would be everything from which the journey began. Earth, the moon, every city, every ocean, every forest, every person not aboard the spacecraft. From 1 light year away, none of those things would be separately visible without instruments far beyond ordinary vision. They would occupy nearly the same direction in the sky, a civilization reduced by distance to the light of its star. There would be no physical line showing where the light year ended. The spacecraft computer might record the moment. A distance estimate would pass a threshold, 1.00 light years from the reference position. Then the number would continue increasing. Outside, nothing would change. The interstellar gas would remain thin. The stars would remain distant. The ship would continue moving. Perhaps that is the clearest way to understand the scale. A light year is enormous to a human being, but the universe does not mark it as enormous. It is simply another interval through space. The drama belongs to us because our lives are short, our bodies are delicate, and our machines must carry every useful thing with them. Light has none of those concerns. It leaves the sun and crosses the distance without fuel, shielding, sleep, food, navigation, or fear of arriving late. 1 year later, it has traveled 1 light year. For anything made of matter, the same distance becomes a much longer story. And somewhere beyond the last familiar boundary of the sun, that story continues through the dark, between stars.